Change of variables, polar coordinates. Our goal in this section is to change double integral, sometimes if it's triple integrals, which we will discuss later, how to change from the rectangular coordinates x and y, dx dy or dy dx region to a polar coordinate region in terms of the radius and theta. So we can go from dx dy or dy dx to dr d theta or d theta dr. Well, let's see if we can compare the region that we want to focus on is this capital R, where it's bounded below by a radius r sub 1 and above by a radius r sub 2. It's bounded below in terms of the angle by theta sub 1 and then above by theta sub 2. So if we can contain the region in terms of x and y in a particular sector as this, then we can convert very smoothly from the rectangular coordinates to polar coordinates. Later on in the triple integral dealing with the so-called space coordinates, we can talk about not just polar coordinates but cylindrical coordinates. And so the cylindrical coordinates would be the same thing as the polar coordinates, but just dealing with x, y, and z, and just not x and y. So the region becomes some set of points r theta. Well, r is bounded below and above by r sub 1, r sub 2, and theta is bounded below and above by theta sub 1 and theta sub 2, according to the graph that we just keep talking about. So the theorem that gives us the change of variables to polar form is let R be a region which is in the xy plane, where x is equal to r cosine theta and y is equal to r sine theta from the polar coordinates, satisfying the conditions that that r is bounded below here by some radius, which is a function of the angle, so g sub 1 of theta, and above by g sub 2 of theta. And here, the so-called radius, it cannot be less than 0, which is the emphasis there. Then the angle is theta is between two other angles, alpha and beta. So g sub 1 and g sub 2, if they're continuous on the closed interval from alpha to beta, and if f is continuous on r, then the double integral over the region of the function with respect to the change in the area is said to be, with its polar form, the integral from alpha to beta, the integral from g sub 1 of theta to g sub 2 of theta, and this is r of x is replaced with r cosine theta, y is replaced with r sine theta. Here the generating factor in the conversion is an r factor, so it's r dr d theta. So if you're going from rectangular to polar coordinates, make sure that you always have this r factor there, r and then dr d theta or d theta dr. Again, just you remember back for the rectangular system for Fabuni's theorem, we talked about vertically simple or horizontally simple. Well, the same thing applies here for the polar form, where you can talk about r simple region or theta simple region. What I would try to do is to keep all of my conversions to the r simple region. Let's look at some problems. The first problem is already given, set up for us, so now all we have to do is just solve it. So it's dr d theta, so that first means for us to integrate with respect to r. We have the integral from 0 to 2 pi. Integrate with respect to r, this becomes 3r cubed over 3, and then r is evaluated from 0 to 6 times sine theta d theta. So now we evaluate the r at the 6. And so that gives us 6 to the third power, and it's times the integral from 0 to 2 pi sine theta d theta. And so here we integrate with respect to the theta. That gives us negative, that's 6 to the third times cosine theta, and that's evaluated from 0 to 2 pi. And so that gives us the negative 6 to the third. The cosine at 2 pi is 1, and then minus the cosine at 0 is 1. And so all we have left is 0. What about the next problem? Integrate first with respect to r, because it's dr d theta. So we have the integral from 0 to power 4, and this becomes r to the third all over 3, where the r is evaluated from 0 to 4. And then we have here sine theta cosine theta d theta. So we evaluate the r at 4, and so that gives us 4 to the third divided by 3 times the integral from 0 to power 4. This is sine theta cosine theta d theta. So here we let u use a u du substitution, so let u equal to sine, and then du picks up the cosine. And so we have 64 over 3 times the integral from 0 to power 4 of u du. That is, let u equal to sine theta, so du picks up the cosine theta d theta. So now we get 64 over, this is u squared divided by 2, so 3 times 2 is 6. And this is the u to be squared, but u was the sine, so we have sine squared theta, and theta is evaluated from 0 to power 4. And so we simplify here. Let's put that in the box. So we have this 64 over, that's 2 times 3, just breaking that down. This is sine of power 4 to be squared. Well, sine of power 4 is 1 over the square root of 2. And that to be squared, here we have 32 over 3 times 1 over 2. And so we get 16 over 3. Okay, let's look a little bit further. We have to use a u du on this 9r square and the r out here. So let's see. So let u equal to 9r squared. And du picks up negative 2r dr. So we have a r dr outside, so negative 1/2 du picks up the r dr. So we use that, put the negative 1/2 out front, the integral from 0 to power over 2, integral from 2 to 3. And this is u, the square root of u, and du, and then out here, d theta. Let's close that up. So we integrate with respect to u. So that gives us u to the 1/2 plus 1 is 3/2. So we have negative 1/2 here, the integral from 0 to power over 2. And this becomes u to the 3/2 divided by 3/2. Now the r was going to be evaluated from 2 to 3. And then out here we have that d theta. Let's simplify that. The 2 goes upstairs, cancels out with that 1/2. So what we have left here is a negative 1/3 times the integral from 0 to power over 2. And the u, you remember, is 9 minus r squared. And that's raised to the 3/2 power. And that form is being evaluated from 2 to 3. And this is d theta out there. So this is negative 1/3 sitting in the front. The integral from 0 to power over 2. We evaluate the r at 3. We get 9 minus 9. That gives us a 0. And then this minus. We evaluate the r at 2. This is 9 minus 2 squared. 9 minus 4. That is 5 to the 3/5 power, or 3/2 power, excuse me, d theta. So on the outside we have positive. Negative times negative is positive, and that's 5 times the square root of 5 all over 3. And this is the integral from 0 to power over 2 d theta, which is just this integral is just power over 2. So we have 5 times the square root of 5 over 3 theta, and theta is evaluated from 0 to power over 2. And so we get our result is 5 pi times the square root of 5 divided by here 3 times 2, or 6. So we get 5 pi times the square root of 5 all over 6. Let's look at some more. In the next couple of problems, the way they're set up is that we have to actually do the conversion ourselves. So here, evaluate the iterated integral by converting to polar coordinates. All right, so let's see what we have. It tells us that the x is bounded below and above by the -2. And the y is bounded below and above here. So 0 less than or equal to y less than or equal to the square root of 4 minus x squared. So this is our region. We want to convert this region to the polar coordinates. And so if you look at this graphically, so x goes from -2 to 2, and y goes from 0 to, this is the top part of the circle with radius 2. So if that be the case, then if you convert to polar coordinates, the radius is 2. And then look at the angle. The angle theta is going from 0, right, to pi. So here, this region, r goes, the radius goes from 0 to 2. So 0 less than or equal to r less than or equal to 2. Now how are we spotting that? Well, here's how we're spotting it. In terms of the radius is bounded from here 0, right? So this is r sub 1, r sub 2. So the radius is going from 0 to 2. Now the angle theta here is going from 0 here, theta sub 2 goes to pi. So the angle goes from 0 to pi. Now this x squared plus y squared is directly r squared for polar coordinates, right? We have that directly, x squared plus y squared is equal to r squared. And so if that be the case, then we convert this double integral. The x squared plus y squared is r squared times the factor of r, you remember, and then we have dr d theta, where r goes from 0 to 2, and theta goes from 0 to pi. So this is the integral from 0 to pi, the integral from 0 to 2 of r to the third dr d theta. Integrate with respect to the r. That gives us 1/4 times the integral from 0 to pi. And this is r to the 4th, and the r is evaluated from 0 to 2. Then out here, all we have is d theta. So that's r to the 4th, or 2 to the 4th. Right. So we have 2 to the 4th divided by 4 times the integral from 0 to pi d theta. So we get 16 divided by 4, and so that gives us here a 4. And then we integrate here, we get theta. Theta is evaluated from 0 to pi, and so our answer is just 4 pi. Okay? Let's look at one more. This square root is across there. So y is bounded here, below and above, and then x is bounded from 0 to 3. Y is bounded here. You see the conversion. It's the same setup from before. Not quite, but let's see what happens. This is x and y. Here, x goes from 0 to 3. And then y is a circle, but it's not the semicircle. It's the fourth sector here, because x is going from 0 to 3. If x was going from -3 to 3, then we have the top sphere, right? So if that be the case, the radius goes from 0 to 3, but theta goes from 0 to pi over 2. The radius is equal to 3. So we say here, this is equal to, this x squared plus y squared is r squared, and that's raised to the 3/2 power times the r factor, dr d theta. R goes from 0 to 3. Theta goes from 0 to pi over 2. We simplify this r squared to the 3/2. That just leaves us with r to the 3rd times r is r to the 4th. So this is the integral from 0 to power over 2, the integral from 0 to 3, and we get here r to the 4th dr d theta. So we integrate with respect to the r, gives us 1/5, the integral from 0 to power over 2, and this is the r to the 5th, and r is evaluated from 0 to 3. Here we get, that's d theta. So we evaluate the r at 3, so that gives us 3 to the 5th all over 5. It's the integral from 0 to power over 2 d theta. So 3 to the 5th, that's 3 squared, which is 9 times 9, 81 times 3, 243. All over 5. And then this is times the theta. The integral of d theta is theta, and theta is evaluated from 0 to power over 2. And so here we get 243 pi all over 10. I think that'll do it for now. Thank you.